So the next question is revision 2, which is on complex numbers still, but the subtopic is de Moivre's theorem. So you are asked to state de Moivre's theorem. Now we can state it by saying for any complex number, for any complex number, okay, what am I writing? Okay, for any complex number in polar form, Z equals to R into cos theta plus I sin theta, and any integer n. So we are looking for de Moivre's theorem, and any integer n, then Z power n is equals to, Z power n will be equals to the all of this particular thing where it is. I think I need to expand this, move this down to have the exact thing. So Z of n will be R into bracket cos theta plus I sin theta, close the bracket for the inner one and the outer one, power n. Now this can be expanded as R power n, then cos n, so let me have bracket here, cos n theta plus I sin n theta. I close that. So that is de Moivre's theorem for any complex number and any integer n. Now we are going to apply this in the next question. The next question, we are asked to use binomial expansion. Then we'll prove that using de Moivre's theorem. All right, so there's work to be done here. Let me give space for that. Now, using binomial expansion, we have Z power 4, which will be, our Z is 2 minus 5I. Now we want to expand this using binomial expansion to power 4. Okay, so for expansion, we'll first list our terms. So our terms will be 2, which is the first term, power 4, and the second term is 5I power 0. So you know in binomial expansion, while the first term decreases or descends, the second term ascends. So we move on. We go to 2, we'll go to power 3 because it is descending, and 5I will go to power 1. Then 2 will go to power 2, while 5I will go to power 2. And then 2 will descend to power 1, while 5I will ascend to power 3. Finally, 2 will descend to power 0, while 5I will ascend to power 4. So at the end, when you add the powers, you get 4. 4 plus 0 is 4, 3 plus 1 is 4, 2 plus 2 is 4, 1 plus 3 is 4, and 0 plus 4 is 4. Now we know if it is a negative, there is an alternative sign. That is negative, positive, and negative, and positive. That is the next thing. Now we need to get the coefficients which are required. So we'll need a coefficient of expansion. Let me use A. I like using A's for coefficient. Or let me use C, if that is okay. So C0, then we need C1 coefficient for that part. And then we need C2 for this part. And then we need C3 for this. And then we need C4. So we can solve this using your calculators, or you can use Pascal triangle. So at least for the better part of the revision, let me upload a Pascal triangle so that we can use to get the coefficients. But calculators can do this very easily. So since I'll be doing it in my calculator, you'll not be seeing it. So let me just use, okay, just somewhere, yes, Pascal triangle should be with me. So I'll just resize it. I'll move it up. Sorry about that. I could have uploaded it earlier, but you can use calculator to solve this. I hope we are able to see what is happening. So I'll move these ones down. So if you look at the Pascal triangle, you can see the coefficients of power 4. So the first coefficient is this one, which is at 0, then coefficient 1, then coefficient 2, coefficient 3, coefficient 4. So coefficient 0 is 1, at 0, at 1 is 4, then at 2 is 6, then at 3 is 4, and then at 4 is 1. So once these coefficients are ready, so we now include them in our expansion. So you have 1, you have 4, you have 6, you have 4 as well, and you have 1. Now we can get our expansions as we move. So the first case, it is 1 times 2 power 4 times 1. You get 2 power 4 is 16. And times 1 is just that, minus. We come to the next part, is 4. Okay, maybe I write it 4 times. This will make me write many things. So it will be 4 dot 2 power 3 is 8 dot 5 power 1 is 5i. Then plus. The next part we have 6 dot 2 power 2 is 4 dot 5i squared. First we squared 5, which is 25, and then we squared I, which is -1. So we are on that. So after negative, we go to plus, under 6, then negative again. Okay. On the negative part, we have 4 dot 2 power 1 is 2 dot 5 power 3 is 125. You multiply 5 times 5 times 5, and I power 3, yes, I squared is -1. Now I power 3 should be negative I. I hope so. Let's see it. I dot I is -1. Now -1 dot I means our I power 3 is -I. Then -I dot I, maybe now power 4, -I times I should be 1. Let me see. Because -I, then first we multiply I times I, which is -1, then times the negative become positive. So this is just I power 4, and this is I power 3, and this is I power 2. Good. So let's come back to our question. So I power 3 should be -I. I'm done with that. Then plus, coefficient is 1 dot, 2 power 0 is 1 dot, 5 power 4 is 125 times 4, should be 625. But let me just confirm that with the calculators. So for the calculator, 6 power 4, not 6, but 5 power 4, 625. So I was right on that. So 625, I power 4 should be 1. I can also express this so that you don't just have 16. So we have 1 dot 2 power 4 is 16 dot 5i power 0 is 1. Now in simplified form, we have 16 So your calculator, so we have 4 times 8, 4 times 8 times 5. 4 times 8 times 5 is minus 160i. Let me see if we have a plus. 6 times 4 times 25. So it will be minus because of the negative 1 there. 600 without I guess. Yes. Then let's see. So we have a negative here, which will create a negative. On this part, we still have a negative. So plus this negative, you get a positive. But what do we have? 4 times 2 times 125i. So it will be 1000i. Then on the last part, we have plus 625. Now, collecting the real part together, so we have 16 minus 600, I guess, then plus 625, then minus 160i plus 1000i. So this part, we have to do it. 16 minus 600 plus 625. This gives you 41. On the other part, we have negative 840, in fact, positive 840i. So, z power 4 using binomial expansion is 41 plus 840i. That is correct with my calculator. So that was really some job done there with the binomial expansion. It is not that easy. So let's find the same, but now with the De Moivre's theorem. The Moivre's theorems tell us that z power 4 will be r power 4 into sine, not sine, but cos, sorry about that, into cos n theta, n is 4, now theta, then plus I sine n theta, n is 4, and then theta. So this is the De Moivre's theorem from the one we stated here. So I just replaced n by 4. Now we need to get r and theta. So what is our z first? Our z was equals to, what was it? 2 minus 5i. Our z was 2 minus 5i. I hope you remember we get theta using tan and r using the modulus. So r is simply the square root of x squared, which is 2 squared, plus y squared, which is negative 5 squared. So when you work this out, you get 4 plus 25, I guess. 4 plus 25 should be 29. So the square root is 29. Then theta, if you remember, is tan inverse of x, the y part, which is our negative 5, over x. I drew this at the beginning. Remember, this is y, which is the opposite, and then this is the adjacent. But I can draw it again. What do we do here? Y is negative, so it's likely to fall in which quadrant? So we have quadrant 1, we have quadrant 2, then we have quadrant 3, and then we have quadrant 4. So when I look at this, this is positive, this is positive, this is negative, and this is negative. So it falls where x is positive and y is negative. So it is in the 4th quadrant. So let me just draw it there so that you see what we mean. So it is here. Now we need this theta here. Now remember, this will be your y, which is negative 5, and then your x is 2. So it matches perfectly. X is positive, y is negative, and this is 90. So this is opposite, and this is adjacent. We apply the tag. But now we need the beta first here, which must be positive. And then we find our theta. So we need beta. Now beta will be tan inverse of now a positive, 5/2. So let's find that out first. So tan inverse of 5/2. So shift tan inverse of 5/2. Okay. Okay, what do I do? Okay, let me change my calculator to degree so that I can work it out. So shift tan inverse of 5/2. Get a small number. I don't know why. Let me check. Oh, okay, I got it. Shift tan 5/2. I was wondering. So the answer is 68.20 degrees. Now, on the fourth quadrant, it is always 360 minus beta. So our theta is 360 minus beta, which is 68.2. When you subtract that from 360, so 360 minus 68.2, we get 291.8. 291.8 degrees. Now we come back to our de Moivre's general equation and solve. So our R, we already know, is root 29 into cos 4 times theta. So let's get 4 theta, which will be 4 times 291.8. So 4 times theta, so times 4, which is 11,1167.2 degrees. Now we have here cos 1167.2 degrees plus I sine 4 times theta again is 1167.2 degrees. Then I close. And remember R is power 4. I was almost forgetting that. So what do we have to expand? We have square, we have open the bracket, root 29, close the bracket, then power 4. When you do that, you get 841 into, now we have cos 1167, cos 1167.2. This gives me 0.049. Let me put it to that. Then plus, now we want sine 1167.2. This gives me 1, approximately 1, which is just I. So when you expand this, what do we get? 841 times 0.049 is approximately 41. Then plus 841 times I will be 841 I. So we get approximate, this was 840, this is 41. So just because of rounding off, but it's approximately there. I think that makes sense. Okay. Okay. We must have the same thing by now. So root 29. Oh. expand times yes, approximately 41.2. So you see, it's almost the same as when you use binomial expansion, which is so accurate. 41 plus 840i. So here we have 841i and 41, we have both sides. So that's it. When you approximate, you get it using de Moivre's theorem. So we have applied binomial expansion and then we have applied de Moivre's theorem. And I need to confirm this using trigonometric identity. You might see, why do we have this error? Because of this rounding off. So let's provide the trigonometric identity. We know that cos 2 theta, this is something we know, is the same as cos squared theta minus sine squared theta, the identities. Then we have sine 2 theta is the same as 2 sine theta cos theta. I just want to apply the trigonometric identity and see if we can get the exact thing. We can see 841 and here we have 41, which is the real number, same for binomial expansion, but now we have 841 instead of 840. So where is this error 1 coming from? So can we avoid rounding off and try to use trigonometric identity? So I'll need to push this down for this proof. Yeah, I need to push that down for the proof. So let's have our triangle. Our triangle was this way, and it had that and this. I'll just use the same thing. So we want to see, why do we have 841? This is -5, if you remember, and this is 2, and this is root 29. And then our theta is here. So let's find cos theta. So using this trigonometric identity, if we have 4 theta, then you simply power this by 4 and power this by 4. I think I need to make sure this is right. This is cos 2 theta, but we have, from the de Moivre's theorem, we have cos 4 theta. So we expect cos 4 theta following the identity to be cos squared 2 theta minus sine squared 2 theta. So for cos 2 theta, we have this identity. So for cos 4 theta, we simply have the same, but now our theta changes to 2 theta because this is twice of this. So 2 theta is this. Twice of 2 theta become, which is cos 4 theta, which is 2 theta sine 2 theta. Now on the other hand, this one, we now want what we need. So sine 4 theta, which we have in the de Moivre's theorem, will now be 2 times, we are now finding the twice. So sine 2 theta is 2 sine theta cos theta, that is the identity. So we need to have here as 2 theta, then cos 2 theta. Let's see where this will lead us to. Just thinking of this to see why we have 841 instead of 840 like the binomial expansion. Now let's find cos theta. So cos theta from our triangle is simply, so this is R, adjacent, opposite, and hypotenuse. So cos is car. So that will be adjacent, which is 2, over hypotenuse, which is root 29. And then sine 2 theta, or sine theta alone, will be equals to, sine theta is so opposite over hypotenuse, -5, which is our opposite, over root 29. Now let's substitute this to our identities. Our identity says that cos 4 theta equals to cos squared 2 theta minus sine squared 2 theta. So this might take us long, but let me see the shortcut. So I have a cos squared theta will simply be into bracket 2 over root 29 squared. This is simply 4 over 29. I think that is fine. And then sine squared theta, we square that, negative 5 over root 29 r squared. Because sine theta is that, so you square. So that gives us 25 positive over 29. Now, we need to get, maybe I can start with the cos 2 theta to make it easier, then we solve for 4 theta. So I need to remove this and also remove this. So when I do that, cos 2 theta will be cos squared theta, which is 4 over 29, minus sine squared theta, which is 25 over 29. This gives us negative 21 over 29. Now let's do the same for the sine 2 theta, so that we'll now extend it to our values we need. So sine 2 theta, on the other hand, will be 2 times sine 2 theta, sine theta, and sine theta is 2 over root 29. No, sine theta is negative 5 over root 29, and negative 5 over root 29 times cos theta, which is 2 over root 29. Now when we work out this, we see 2 times negative 5 times 2 will be 4 times negative 5, which is negative 20, divided by 29, because root 29 times root 29 is root 29 squared, which we can obtain as that. Now what we need is cos into bracket 4 theta, which is the same as cos squared 2 theta minus sine squared 2 theta. Cos squared 2 theta, but cos 2 theta is here. I think I need to make sure this is clear. Cos 2 theta is this. So if you square it, it will be into bracket negative 21 over 29 squared minus, so cos squared 2 theta minus sine squared 2 theta. Sine 2 theta is negative 20 over 29. So we have negative 20 over 29, again squared. So when you work this out with your calculator, so we have into bracket negative 21 over 29 squared minus into bracket negative 20 over 29 squared. And then I get 41 over 81. This gives me 41 over 841, sorry, over 841. Now let me do the next part. The next part we have sine 4 theta. Now sine 4 theta, we already have sine 2 theta. So sine 4 theta is simply, sine 4 theta is simply twice that. So we already have sine 2 theta as 2 negative 5, which gives us negative 20 over theta. Wait a minute. So that is sine 2 theta. Okay. Now we need our sine 4 theta, which is 2 sine theta times cos theta. So 2 times sine theta, which we already have, to negative 29 over 20, negative 20 over 29. Then times cos 2 theta. Cos 2 theta is also here. So we have this as 2 into sine 2 theta, which is negative 20 over 29, times cos 2 theta, which is negative 21 over 29. So what does this give us? using my calculator is 2 into, you simply add the top, which is negative. Okay, let me just work it out. 2 times negative 20 over 29, close the bracket, times into bracket, negative 21 over 29. Close the bracket. Then, okay, that one goes. So let me do it again, negative 20 over 29. Close the bracket, times negative 21 over 29, close the bracket. And then we get it as 840 over 841. 840 over 841. Now De Moivre's theorem. We said z power 4 equals to our root 29 power 4 into sin, not sine, but cos, into cos 4 theta, remember, then plus I sine 4 theta. Just want to know why the different come. But you'll not be marked right. The difference is very small because of rounding off the angles here. But I just express 4 theta, sine 4 theta, and cos 4 theta and sine 4 theta using trigonometric identity. So I will just substitute in this. We already know that root 29 power 4 is 841. And we already know that cos 4 theta is here, which is 41 over 841. Then plus I sine 4 theta, which is 840 over 841. Now you see we get the correct thing, like we get exact thing like the binomial expansion, because when you multiply 841 times this, it will cancel 841, we get 41. Then plus 841 times this, it will cancel 841, then we get 840i, which is exactly the same as this. So the one here comes because of rounding off in the angles, but you can get the exact value by using the trigonometric identity. So if you forget this, then just go through this method. You'll get an error of 841 in the imaginary, that is an error of 1, which can still be ignored. But using the trigonometric identity proves is that our binomial expansion, which is 41 plus 840i, is actually correct. That was a long journey to reach there, but finally we are there. So we can proceed to C. Now C, okay, let's just... So C tells us for all complex roots of the equation z power 4 equals to negative 8, I 8 power 3, express the answers in polar form, r cos theta plus I sin theta. So that is what we have on that. So the first thing we're going to get is r, and then theta. So we have z power 4 is given by negative 8 plus I8 root 3. I can rub this I just to maintain this, but there's no problem in writing it in front or behind. It's okay, that's okay. So let's get R. So R first, we are going to find R by doing the square root of x squared, which is negative 8 square, plus y squared, which is 8 root 3 r squared. Now this is equivalent to square root of 8 squared is 64, then plus, here you square 8 and square root 3. So 8 squared is 64, then 64 times 3. So when you do that, you have 8 times root 3 squared is 3, you get 192. So 1 92. When you add 192 plus 64, you get square root of 256, which is just 16. Now we need theta. I hope now you know how we get theta. So theta is tan inverse of y over x. Let me write the formula, which is tan, y is opposite over x adjacent. Tan inverse of our y is 8 root 3 over negative 8, which is simply tan inverse of negative root 3. So you can see we have negative 8 and 8 root 3. So this is in which quadrant? Let me put something here. This is x and this is y. So x is negative, y is positive. So this is probably in the second quadrant, where we have 180 degrees minus our acute angle beta. Because y is positive, x is negative. So let's get beta and less from 180. So beta is tan inverse of root 3, which is just 60 degrees. Think so? Can try shift tan inverse of root 3, 60. And if you like, this can be given as pi over 3 in terms of radians. Now we have beta. So our theta is in the second quadrant. So it is 180 minus 60, which is 120 degrees. If you like, 2 pi over 3. Good job. Now we have done that and we are happy. So we have everything. Now our W, which is our root, will be expressed as W, which is our root, will be expressed as our R. Remember, we were told R cos theta plus I sin theta, and R is 16 into bracket cos 120 degrees, then plus I sin 120 degrees. If you like, you can use radians by saying 16 into bracket cos 2 pi over 3, then plus I sin 2 pi over 3. We need to make sure this is nice. We have a long way, but we'll just be done, don't worry. Just need to have correct thing done. Now, we'll apply De Moivre's theorem of roots of complex numbers in order to get the roots of this. Now, it states that zk, of course, we are now reversing the De Moivre's theorem, is 1 over n. Remember, it was power n here. And then into bracket, we are reversing the normal De Moivre's theorem. So we have theta plus 2k pi over n, and then plus I sin, same thing, theta plus 2k pi over n. And then I close this, where k, 0, 1, 2, 3, and this can go to n minus 1. So that is how we get k. Okay, so our n already we know. N is 4 because it was z power 4. Our r we already know, 16. We calculated that. And our theta we calculated to be 2 pi over 3. So work must be done. So we are going to get thetas, or the angles, at k equals to 0, like that, like that, like that, as we proceed. And remember, our n is 4. Okay, so let me see if we can have enough space here. Okay, let me talk about the complex roots on Z1 and we move with K. So let me just remove this one. So K start from 0. Our N is 4 and everything. So let us now get our complex roots. So Z0. Remember R is power 1 over N. I think I need to do that to avoid repeating that. So R is power 1 over N, which is just 16 power 1 over 4. The fourth root of 16 is 2. 2 power 4 is 16. So once that is done, I can now move. From this formula, my R will be 2 because it's power 1 over N. Then the first root will be cos. You are substituting K with 0. That is what we are doing. When you substitute K with 0, the whole of this term will be 0. You can see, because 2K will be 20 times pi. Now you'll remain with your theta alone over N. So you'll remain with your theta you know, which is 2 pi over 3 over N, which is 4. Then plus, same thing for the complex part, sine 2 pi over 3, which is our theta, over 4. So this will be simplified to 2 into bracket cos. Let me see. 2 divided by that is 2, so we have just pi over 6. I hope you are able to see that. Plus I sine pi over 6. Remember, our limits were from negative pi less than or equals to theta, less than or equals to pi. So as long as the value of pi we are getting here, the value of theta we are getting is less than pi or greater than negative pi, then we are good to go. So pi over 6 is less than pi. So that is, it is not outside the limit. Now we go to Z1, but let me do this. I need a space. Okay, sorry about that. Let me move this one down. Yeah, space is necessary. Okay, long work. So we have Z1 will be equals to, still remain 2, but now what will be our cos? Cos theta is our 2 pi over 3, then plus, now k is 1, so 2 times 1 pi will be 2 pi. Then all this you divide by 4, plus I sine, same thing, 2 pi over 3 plus 2 pi, all divided by n, which is 4. Then the whole thing is under the big bracket. So let's work out this part. Now you have 2 pi over 3 plus 2 pi. So if you want them to be over 3 all, then we can have 6 pi over 3. So let me solve this part. So 2 pi over 3 plus 6 pi over 3. Remember, 6 pi over 3 is 2 pi. So when you solve this, you get 8 pi over 3. I think that is what you should get. And then this 8 pi over 3, you divide by 4 again, which gives you 8 pi over 12. You simplify this, 2, 4 goes there 3, so 3 pi over 4. Wait, 4 goes into 8 2 times, then 4 goes into 12 3 times. So it is 2 pi over 3. So it is 2 pi over 3. Now, your root is simplified as 2 into cos theta, which is 2 pi over 3 plus I sine 2 pi over 3. Good. So 2 pi over 3 is still less than pi because 2 pi over 3 is around 120, which is less than 180. So Z1 root is still valid. Remember, we are getting the roots up to power 4, root up to 4, because Z1, we have Z0, Z1, Z2, and Z3. Z3 will be our last. So we go to Z3, Z2. Now Z2 will be 2, then we have cos. Our theta, which is 2 pi over 3 plus k is now 2. So when you put 2 in k here, you have 2 times 2, 4, then you have 4 pi. So I have 4 pi here. That one close, then plus I sine into bracket 2 pi over 3 plus 4 pi, because now k is 2. Now all this over 4 and also this over 4. We'll solve again and simplify. So we'll solve and simplify. So let's see. Now we have 2 pi over 3 plus 4 pi to make it over 3. 4 goes to what? 3. 3 goes into what 4 times? I think 12 pi over 3. 12 pi over 3 is the same as 4 pi. 3 goes into, yeah. So when you add, you get 16 pi, not 16, but 14. Now when you add, you get 14 pi over 3 over 4. Now this is simplified to 14 pi over 12. 2 goes there, 7, and then over 6. You can see this is greater than 180. This is like 7 times 6 times 180. 6 goes into 180 3 times 3. That is 30 times 7 is 210. So since it is greater than 180, it is out of bound. So we less 2 pi. So 7 pi over 6 is out of bound. We less 2 pi to return it to within the bound, which is just 7 pi over 6 minus 2 pi will be 12 pi over 6, so that we can subtract easily. And that will be negative 5 pi over 6. So our other root, which is Z2, will be 2 into cos into bracket negative 5 pi over 6 plus I sine 5 pi negative 5 pi over 6. So that is now valid. Now our last root is Z3. Now there will be 4. So Z3, where k is 3. So this will be cos, remember 2 pi over 3, which is our theta, plus we go to the general formula. Now we replace k here to be 3. 3 times 2, 6. 6 pi. So we have 6 pi. So we have 6 pi, and the whole thing over 4. Remember n is 4. Then plus I sine into bracket the same thing, 2 pi over 3 plus 6 pi all over 4. Close, and then the big bracket. So we need to simplify this again and check if it is out of bound. If so, we need to subtract 2 pi. Now let's do that. So we have 2 pi over 3 plus 3 goes into what 6 times? 18, I guess. So 18 pi over 3. If you divide 3 by 18, you get back your 6 pi. So to add it easily, you have 20 pi over 3, then all this over 4. This gives you 20 pi divided by 12. Simplified by 4, 4 goes there, 5 pi, and 4 goes into 12 of 3. Again, this is greater than pi because it's 5 over 3. So when you want to reduce this, again, you minus 2 pi. So 5 over 3 minus 2 pi, which is same as 2 pi will be the same as 6 pi over 3. Remember, this is just 2 pi. You are subtracting. So 6 over 3, you minus 2 pi. So since we have same base, we just subtract up, we get pi over 3. Now, our root, the last root is Z3 equals to 2 into cos theta, which is negative pi over 3 plus I sin theta, which is negative pi over 3. And that's all. So we have our roots, which bounded from negative pi to pi. Long job, but worth it. So that is how we solve such kind of problem. The roots of complex number using De Moivre's theorem. Now we need to go to the last question, which is this. So use De Moivre's theorem and binomial expansion to do this, to show that cos 3 theta is the same as 4 cos cube theta minus 3 cos theta. So what is the binomial expansion of this? So De Moivre's theorem says z, let's start with De Moivre's theorem, z power 3 is the same as r power 3 into, I think we need to, let me. Okay, we were not told, so it's like r is 1. So I'll just continue to write that, cos 3 theta plus I sine 3 theta. But we are not given r, so it is 1. So the answer is just into bracket cos 3 theta plus I sine 3 theta. Now using binomial expansion, we can use the expansion as cos theta plus I sine theta, then cube. We can compare that with a plus b cube. We know that a plus b cube is a cube, it's a standard expansion, plus 3a squared b plus 3ab squared, then plus b cube. But I can show this, you don't need to cram this. You can show this by simply saying a power 3 while b power 0, a power 2 while b power 1, a power 1 while b power 2, a power 0 while b power 3. From our coefficients of expansion, 1, 3, 3, 1. Then when you put that together, you get a cube, b power 0 is 1, plus 3a squared b, then plus 3ab squared, then plus b cube, because a power 0 is 1. So it's just the same thing. You don't need to cram that, just use the normal expansion. So applying that to our problem, so our a, from that, we know that our a is cos theta, and our b is I sine theta. So let's move. So a cube, we have cos theta cube plus 3 into a squared cos theta squared times b, which is I sine theta, then plus 3 into a, which is cos theta, times b squared, I sine theta squared, then plus b squared, which is I sine theta cube. Okay, so this will give us cos cube theta plus 3 cos squared theta, then sine theta, if you like, I, the whole thing, then plus 3 cos theta. Then when you square I, it becomes a negative. So we have a negative here, while now we have sine squared theta. Then finally, plus, it will be a negative. When you square I, it becomes a negative. So it will be a sine cube theta I, because I cube is negative I. So we have cos cube theta plus 3 cos, if you like, we can put I in front, I 3, let me just maintain it. So plus 3 cos squared theta, then sine theta. The whole thing here is I. So we can pull I together. I think that was the best thing. Let's bring the real part together and the imaginary part together. So we have cos cube theta, and the other real part is this. So it is a minus. So minus 3 cos theta sine squared theta. This is the real part. Now, plus the imaginary part, the other part, the first part is 3 cos squared theta sine theta, then minus sine cube theta, and the whole thing into I. So we were told that the real part which we have there must be equals to cos 3 theta. That is what we know. For in a complex number, they must be equal. So we are told there that cos 3 theta is equals to the real part, which we have 4 cos cube theta, but we need to prove that that part is equals to this. Now or I can rather say it, for complex numbers to be equal, their real part must be equal. So this part here, 3, okay, cos 3 theta, and let me write in blue. Now this part, which is cos 3 theta, must be equals to our real part. This is our real part, and this is our imaginary part. So for complex numbers to be equals, you must you equate their real parts or complex parts. So the real parts must be equal. So what we are given here is a real part, because we don't have I. So the real part cos 3 theta must be equals to our real part here. And our real part here is cos cube theta minus 3 cos theta sine squared theta. Now we need to express this. Using the Pythagoras theorem of trigonometry, we know that sine squared theta plus cos squared theta equals to 1, meaning sine squared theta is just 1 minus cos squared theta. So we are going to have cos 3 theta to be equals to cos cube theta minus 3 into cos theta, then again sine squared theta, which is 1 minus cos squared theta. We have substitute sine squared theta. So this will be cos cube theta minus 3 cos theta, then plus, because of negative, negative, so we have plus 3 cos cube theta. Because this is 3 cos theta times cos squared theta, become 3 cos squared theta, cos cube theta. So you collect like terms. Cos cube theta plus 3 cos cube theta is 4 cos cube theta minus 3 cos theta. So we had 4 cos cube theta minus 3 cos theta, which is exactly the same. So we have proved that. We have proved that this is the same as this, because this compared to our real part, which was this, then using trigonometric identity, the Pythagoras theorem, we substitute for this, and then we rearrange by expanding 3 cos theta times 1 plus 3 cos theta times cos squared theta. Then put together, you get 4 cos cube theta minus 3 cos theta, which is exactly equals to this. So we have used De Moivre's theorem and binomial expansion to show this. And that marks the end of revision 2. It was so long, but it worth it. It was not that easy to go through. And I hope you will learn something from this. In fact, if you have any question or any mistakes, simply put it on the comment section. I can go through that and then correct where necessary. Or if you like the lesson, you can also hit like. Also, you can subscribe to support my channel. Thank you.